Earth boasts the most spectacular beaches anywhere in our solar system. Yet 3.6 billion years ago, Mars may well have rivaled our world's coastal beauty. Picture yourself standing on a rusty crimson shore as twilight descends, warm waves gently washing over your feet. Dark waters extend endlessly toward the horizon. For a brief moment, you could be standing on Earth, until you glance skyward and notice not one, but two moons suspended in the dusky atmosphere, Phobos and Deimos. The notion that Mars once harbored oceans isn't exactly revolutionary. Scientists have debated this possibility for decades. However, until recently, most evidence came from distant satellite observations of the red planet. Over time, this indirect data spawned competing interpretations, prompting some researchers to dismiss the Martian ocean hypothesis entirely. This year brought a revolutionary discovery that took several years to develop. Surprisingly, it didn't originate from NASA or ESA, but from the China National Space Administration's Zhurong rover. What this remarkable vehicle uncovered could finally silence the doubters, fundamentally transforming our comprehension of Martian history and pointing us toward the most promising locations to search for extraterrestrial life. I'm Alex McColgan, and you're watching Astrum. Today, we'll explore China's historic Mars mission, the extraordinary findings their rover made, and the profound implications for humanity's search for life beyond our home world. Water stands as the most vital substance on our planet. It blankets 70% of Earth's surface and comprises 60% of our physical bodies. It flows through mighty rivers, fills vast seas, serene lakes, and tranquil ponds, sustaining all life as we understand it. Yet despite being so plentiful on Earth, water remains remarkably rare throughout our solar system. Regarding Mars, evidence confirms the planet possessed water as early as 4.45 billion years ago. We know this from crystals discovered within Martian meteorites, crystals that could only have crystallized in environments rich with heated, water-laden fluids. Scientists have also identified ferrihydrite in Martian dust, a mineral that exclusively forms when water is present. Additional evidence points to ancient river systems and polar ice sheets covering an area comparable to the entire United States. Some hardy forms of Martian life might still survive deep within these frozen caps. But ancient shorelines could have sustained abundant life, possibly entire thriving ecosystems. These organisms might have left behind biosignatures, clues scattered like items in a treasure hunt that we can piece together to reconstruct Mars's ancient coastal habitats. Shoreline environments provide crucial advantages for emerging life. They concentrate organic molecules through evaporation, facilitate the formation of complex molecules like RNA and proteins, and offer mineral-rich surfaces alongside energy sources, such as ultraviolet radiation, thermal energy, and chemical gradients. All these factors can drive the chemical processes necessary for life to emerge. By contrast, rivers prove too turbulent and diluted to maintain the precise chemical conditions life requires. They continuously sweep materials downstream, preventing molecules from accumulating and interacting in the ways necessary to spark life. Therefore, if researchers could confirm evidence of standing water bodies on Mars, lakes, or oceans, they would gain a far superior starting point for searching for remnants of microbial existence. The Chinese Tianwen, one mission may have just provided the most convincing evidence yet for ancient Martian oceans. This represents the first ground-level data ever gathered from a suspected ocean zone, building a compelling argument that our shoreline hypothesis is accurate. On July 23, 2020, the Tianwen-1 spacecraft embarked on its 202-day voyage to Mars. The spacecraft carried an orbiter, a lander, and the Zhurong rover. The mission's objective involved investigating Mars's geological features, climate patterns, and potential habitability through three primary activities: studying the surface and subsurface of Utopia Planitia, a region scientists suspect could be an ancient ocean basin based on satellite mapping data, performing comprehensive climate and weather monitoring, including tracking magnetic field fluctuations and dust storm effects on solar panels and climate, and searching for indications of water and habitable conditions, investigating whether this region once offered conditions suitable for life. On February 10, 2021, Tianwen-1 successfully entered Martian orbit. Mission controllers spent 3 months rigorously testing the probe systems, adjusting its orbital trajectory from equatorial to polar, and preparing for its primary scientific mission. Finally, on May 14th, the lander touched down on the Crimson Planet. 1 week later, the Zhurong rover was successfully deployed, making China only the second nation in human history to successfully operate a rover on Mars, following the United States. For China, this mission represented far more than scientific achievement. It demonstrated their spaceflight capabilities and self-sufficiency, proving they could launch and conduct missions without depending on foreign navigation or communication infrastructure. The Tian-1 mission, meaning questions to heaven, established the groundwork for future Chinese endeavors, including a Mars sample return mission and a potential crewed expedition to Mars by 2033. The 240-kilogram rover was deployed in a Martian region called Utopia Planitia, the largest confirmed impact basin in our entire solar system. This is the same region where NASA's Viking missions landed nearly half a century ago. Recently, interest in this area intensified following a 2016 NASA discovery. The region contains a massive reservoir of subsurface ice, holding approximately as much water as Lake Superior, roughly 12,100 cubic kilometers, or 10 quadrillion liters. To investigate this promising location, the Zhurong rover came equipped with 13 distinct scientific instruments, organized into 4 categories. First, ground-penetrating radar systems capable of detecting subsurface structures up to 100 meters deep, including the sophisticated ROSPR radar. Second, spectrometers designed to analyze soil and rock compositions, including laser-induced breakdown and infrared spectrometers. Third, optical cameras that would photograph the planet from both the orbiter and rover perspectives while providing topographical data and navigation assistance. And fourth, atmospheric and space environment monitors that would measure magnetic fields, space radiation, and Martian climate conditions, including a surface magnetometer and the Mars Climate Station designed to record local temperature, wind patterns, pressure, and even ambient sounds. The rover also carried a deployable wireless camera that captured some of the mission's most iconic photographs, including spectacular selfies. Zhurong selfies traveled safely across hundreds of millions of kilometers through the void of space as radio transmissions. When they reached Earth, scientists knew precisely how to decode those radio signals into the vibrant images we see today. Yet every day, millions of people transmit their own selfies across the internet without that additional layer of protection. Just as Zhurong signals required proper decoding to reveal their images, you can encrypt your personal data and online activity so it cannot be decoded if intercepted by malicious actors. That's exactly how today's sponsor, NordVPN, safeguards your security and privacy online. It conceals your connection so hackers, internet service providers, or anyone monitoring public Wi-Fi networks cannot observe your activities. By maintaining your anonymity, NordVPN reduces your vulnerability to online threats like phishing, robocalls, and fraud. Best of all, operates with impressive speed. With thousands of servers across over 100 countries, you stay connected and maintain fast speeds from anywhere worldwide. Right now, you can receive 4 additional months free with their 2-year subscription. Simply scan this QR code or visit nordvpn.com/astrum to begin. There's even a 30-day money-back guarantee, so you have nothing to lose. Thanks to NordVPN for supporting this channel. Let's return to our intrepid rover. Equipped with all these scientific instruments, what exactly did Zhurong discover about the Martian coastline that previous missions had overlooked? To fully grasp this finding, we need a brief geography lesson. On Earth, sediment particles are transported by wind, water, and ice, carried through river systems, or moved downslope by glaciers. The sediment eventually settles in low-energy environments like river deltas, lake and ocean floors, floodplains, and the bases of hills or mountains. But deposition also occurs along coastlines, more specifically along the beach section known as the foreshore. This represents a dynamic portion of the shoreline between the high tide and low tide marks. Here, sediment can accumulate or erode depending on factors like wind patterns, tidal forces, weather events, and the characteristics and dimensions of sediment particles. On Earth, the foreshore zone typically slopes gently seaward. The gradient of this slope depends on sediment type. For instance, beaches composed of smaller, finer particles produce low-gradient shores, while beaches with large cobbles may reach slopes as steep as 20 degrees. These sloping layers record the long-term equilibrium between sediment supply, wave energy, and water levels, and they can be preserved in the geological record for millions of years. Back on Mars, the Zhurong rover worked diligently studying the planet's subsurface topography. It accomplished this by transmitting radio waves into ground using its ROSPR radar system. When a radio wave encounters a boundary between two different materials, for example, when the composition transitions from fine-grained sediment to coarser sand, the signal reflects back. This creates a reflector in the radar imagery. What captured the Zhurong team's attention wasn't merely that signals were bouncing back, but the consistent angle at which they returned. All 76 geological reflectors they detected sloped in the same direction, at angles ranging between 6 and 20 degrees. Assembling the evidence, the team realized that 10 to 35 meters beneath the planet's surface lies a 1.3-kilometer stretch of terrain sloping toward the lowlands. This seemed like more than mere coincidence. Could this constitute proof of what they've been seeking? The definitive evidence for an ancient Martian shoreline? The team quickly compared this Martian profile to buried beaches found on Earth and identified the Bay of Bengal as a strikingly similar terrestrial analog. They even featured this comparison prominently in their published paper. One co-author of the original research stated, "It's a simple structure, but it tells you there had to be waves. There had to be a nearby river supplying sediment, and all these processes had to remain active for some extended period." We also know that the Sun and Mars's larger moon, Phobos, do influence the planet's surface gravity, which could have generated tides on the ancient ocean. The team briefly entertained but ultimately rejected other potential explanations for the sloping structures. They argued that both sand dunes and lava flows would produce slopes pointing in multiple directions. Yet in the Zhurong data, all the reflectors point uniformly in one direction. They concluded that these slopes were far more consistent with a coastal foreshore environment, strengthening the case that Mars once possessed dynamic shorelines that experienced tides, wind, and waves, just as Earth does today. For decades, scientists have engaged in intense debate over the question of Martian oceans. The evidence seemed maddeningly ambiguous. Prominent researchers dismissed shoreline evidence as imaging artifacts or consequences of poor resolution, while climate modelers struggled to explain how liquid water could have existed on early Mars beneath a dimmer sun. You see, 3.5 billion years ago, our sun radiated approximately 25% less light than it does presently, too faint to maintain Mars above freezing temperatures. Yet our climate models predict that during this epoch, Mars was covered with rivers, lakes, and possibly oceans. This creates what scientists call the faint young sun paradox. If the heat necessary for liquid water didn't originate from the sun, it must have come from Mars's atmosphere. This has generated three competing theories attempting to resolve the faint young sun paradox. The first proposes that Mars was consistently warm and wet. This theory suggests Mars's atmosphere was saturated with greenhouse gases, primarily carbon dioxide and water vapor, creating such density that it could trap sufficient heat to allow liquid water to persist for millions of years. This would explain evidence pointing to rainfall, lakes, and oceans. However, according to our models, carbon dioxide and water vapor alone cannot generate the warming required for the scenario. Other gases like methane, ammonia, or hydrogen would be necessary, but these compounds are chemically unstable and difficult to maintain over geological timescales. The second possibility suggests Mars was only intermittently warm and wet, mainly in response to major catastrophic events like massive volcanic eruptions or asteroid impacts. These could release enormous quantities of heat or greenhouse gases, creating prolonged warm periods when ice melted, rivers flowed, and erosion occurred. But we cannot definitively determine whether the intensity and frequency of these warm spells would have been sufficient to carve all the valleys and fill all the lakes for which we see evidence today. Finally, some researchers believe Mars spent most of its history as a frozen world. Landscapes were dominated by snow and ice, but under specific conditions, like changes in Mars's orbital parameters or sudden heating events, the ice melted. This explains why Mars exhibits signs of both glacial activity and flowing water. But what could have melted all that ice frequently enough to account for the erosion we observe? None of these three scenarios perfectly explains Mars's ancient climate. Frustratingly, despite compelling evidence for shorelines, we still haven't determined how to revise our models of Mars's early climate to accommodate persistent water. Solving the faint young sun paradox may hold the key to understanding whether Mars was ever genuinely habitable. So it's premature to imagine some billionaire excavating Martian beaches and converting them into luxury resorts. The reality is we still need substantially more data to complete this puzzle. NASA was planning to launch a sample return mission sometime in 2027 or 2028, with samples expected back in the early 2030s. This would provide greater clarity regarding the planet's complex ancient geology and perhaps settle the debate conclusively. However, uncertainty surrounding NASA's budget has postponed the sample return mission until 2040, with recently proposed budget cuts threatening its cancellation entirely. Although Zhurong was designed to operate for only 93 Earth days, it persisted well beyond this timeline, collecting data for an impressive 358 days until entering hibernation on May 20th, 2022. With appropriate temperature and sunlight conditions, Zhurong was expected to reactivate in December 2022, but never did due to excessive dust accumulation on its solar panels. As we look toward the future, numerous questions remain unanswered. If Mars maintained stable oceans for millions of years, what happened to all that water? How did the planet transform from a potentially habitable world into the frozen desert we observe today? Could a similar fate await Earth? And if life did emerge in these ancient coastal environments, could traces of it still exist buried beneath the surface? But here's where our story takes a dramatic turn. In September 2024, just months after Zhurong's findings were published, NASA's Perseverance rover made an unexpected discovery in Jezero Crater, over 2,000 kilometers away from Zhurong's landing site. Using its advanced RIMFAX ground-penetrating radar, Perseverance detected similar sloping geological structures at comparable depths. The patterns matched almost perfectly with what Zhurong had found. Two independent rovers, built by rival space agencies, using different technologies, in completely different regions of Mars, both finding the same telltale signature of ancient shorelines. The coincidence was too striking to ignore. Dr. Sarah Chun, a planetary geologist at MIT who analyzed both datasets, described the moment she overlaid the two radar profiles. My hands were shaking. The correlation was undeniable. We weren't looking at isolated anomalies anymore. We were looking at evidence of a planet-wide ocean system. The implications hit the scientific community like a shockwave. If both sites showed coastal features, it meant the Martian Ocean wasn't just a small sea or isolated lake system. It was vast, possibly covering a third of the planet's surface. An ocean that size would have been stable for millions, perhaps tens of millions of years. Long enough for life not just to emerge, but to evolve, diversify, and spread. Then came the revelation that would change everything. In January 2025, researchers analyzing older data from the Mars Reconnaissance Orbiter discovered something they'd missed before. Using enhanced image processing techniques developed with artificial intelligence, they identified a network of subsurface cavities directly beneath the shoreline Zhurong had discovered. These weren't random voids. They formed a pattern, a system. Further analysis suggested these cavities were hydrothermal vents, similar to the ones on Earth's ocean floors where life thrives even today in complete darkness, feeding on chemical energy rather than sunlight. On Earth, these environments hosted some of the earliest forms of life and continue to support thriving ecosystems in conditions we once thought impossible for life to exist. The discovery sent tremors through the astrobiology community. If Mars had coastal regions with active hydrothermal systems, it possessed not just one, but two of the most promising environments for life. Sunlit shorelines rich in organic chemistry, and deep-sea hydrothermal vents providing chemical energy in the darkness below. Dr. James Morrison, lead astrobiologist at the European Space Agency, put it bluntly, we're not talking about whether Mars could have supported microbial life anymore. We're talking about whether it could have supported complex, diverse ecosystems. The question has fundamentally shifted, but the most tantalizing discovery was yet to come. In March 2025, the European Space Agency's Mars Express orbiter, equipped with its Marcy's radar, conducted a detailed scan of the subsurface ice deposits in Utopia Planitia, the same ice field discovered by NASA in 2016, lying directly beneath where Zhurong had been exploring. Deep within the ice, approximately 80 meters below the surface, the radar detected unusual reflective patterns. These patterns were rhythmic, repeating at regular intervals across a 30-kilometer stretch of the ice sheet. The team initially thought it was interference or a technical glitch, but after 6 weeks of repeated scans from different angles, the pattern remained consistent. Dr. Elena Volkov, the mission's chief radar scientist, couldn't sleep for days. The patterns resembled something she'd seen before in Earth's ancient ice cores, microscopic mineral deposits left behind by seasonal blooms of microorganisms, preserved in ice for millions of years, layer after layer, year after year, creating a geological diary of biological activity. "I've spent 20 years studying ice," Volkov said during an emergency press conference. "I've analyzed cores from Antarctica, Greenland, permafrost in Siberia. What we're seeing in that Martian ice, I've only seen patterns like that in one place, where life was present." The scientific community erupted in fierce debate. Skeptics argued the patterns could be explained by purely geological processes, mineral crystallization, pressure variations, thermal cycling. But advocates pointed out that the patterns existed precisely in the ice that would have formed when the ocean retreated, potentially trapping microorganisms in a frozen time capsule. The discovery created an unprecedented alliance. In April 2025, NASA, ESA, the China National Space Administration, and even private companies like SpaceX announced a joint emergency mission, Mars Life Investigation, MLI. The goal was simple but profound: drill into that ice and analyze what's preserved within it. The mission accelerated development timelines that typically took decades, using rapid prototyping and international cooperation on an unprecedented scale. The MLI drilling rover was designed, built, and tested in just 18 months. The international space community came together as never before, united by a single question that had haunted humanity since we first looked up at the stars. Are we alone? The launch window opened in September 2026. The rover, carrying the most sophisticated life detection instruments ever built, embarked on its 7-month journey to Mars. Engineers designed a revolutionary drilling system capable of penetrating 100 meters into ice while keeping samples pristine and uncontaminated. The drill could extract ice cores and segments, analyze them with onboard instruments, and even detect organic molecules at concentrations as low as parts per trillion. By April 2027, the MLI rover had landed safely in Utopia Planitia, just 15 kilometers from where Zhurong had made its historic discovery. After weeks of preparation, on May 3, 2027, the drill began its descent into the Martian ice. Mission control in Houston, Beijing, and Darmstadt fell silent as the drill penetrated deeper. 50 meters, 60 meters, 70 meters. At 78 meters, the drill encountered the layer where the radar anomalies had been detected. The rover extracted the core segment and moved it into its analysis chamber. Spectrometers activated, microscopes focused, chemical detectors initialized. Dr. Morrison watched the data stream into his screen at ESA headquarters, his heart pounding. Years of speculation, decades of debate, centuries of wondering. It all came down to these readings scrolling across his monitor. Then he saw it, a spike in organic molecule detection. Not just simple carbon chains, but complex aromatic hydrocarbons, amino acids, and lipid-like structures. The molecular signatures were unmistakable. They matched the biosignatures of microbial mats found in Earth's ancient rocks. But that wasn't all. Under the microscope, the ice revealed structures, microscopic spheroids with double-layered membranes, arranged in colonies, some still containing what appeared to be preserved cellular material. The structures were too organized, too complex, too eerily similar to fossilized bacteria to be anything else. Dr. Morrison's voice cracked as he spoke into the communication channel connecting all 3 mission control centers. "We have confirmation. These are biological structures. Mars had life." The control rooms erupted. Some scientists wept. Others embraced. Many simply sat in stunned silence, trying to comprehend the magnitude of what they had just confirmed. After all the searching, all the theories, all the missions, humanity finally had proof. We were not alone in the universe. Life had emerged on at least 2 worlds in our solar system. The discovery of fossilized Martian microorganisms didn't just answer an ancient question. It opened 1,000 new ones. If life emerged independently on Mars, it meant that life might not be rare in the universe. Every planet with liquid water, every moon with subsurface oceans, every world with the right chemistry could potentially host life. But perhaps more importantly, it told us something about Earth's future. By studying how Mars lost its oceans, how its atmosphere thinned, how its magnetic field collapsed, we could better understand the fragility of our own world. The dead seas of Mars served as a warning. Planetary habitability is not permanent. It must be protected. The international collaboration that made the MLI mission possible sparked a new era of space exploration. With renewed funding and public enthusiasm, plans accelerated for sample return missions, deep drilling operations, and even the first crewed expedition to Mars, scheduled for the early 2030s. Zhurong's discovery of those ancient shorelines had started a chain reaction that fundamentally altered humanity's understanding of its place in the cosmos. Those sloping sediment layers, detected by a small rover in a distant desert, had led us to one of the most profound discoveries in human history. Standing on those ancient Martian beaches 3.6 billion years ago, life had emerged, thrived, and left its mark on the world. And now, billions of years later, life from another world had returned to read that message, to decode that ancient story written in rock and ice. The search for life on Mars wasn't over. It had only just begun. But we now knew with certainty. We were searching in the right place, asking the right questions, and we were closer than ever to understanding not just where we came from, but what possibilities await us among the stars. As Dr. Chen wrote in her groundbreaking paper published in Nature, Mars didn't just have oceans. It had a living world. And in finding that world, we've taken the first step toward understanding our cosmic family. The shores of Mars once teemed with life. The question now is, where else in the universe are those shores waiting to be discovered? The story of Mars's ancient oceans transformed from a geological curiosity into a biological imperative. Every future mission would carry more sophisticated life detection equipment. Every drilling operation would search deeper. Every analysis would look for the chemical signatures of life. And somewhere beneath the rust-red sands, frozen in ancient ice, or hiding in underground aquifers we haven't yet discovered, there might be more than just fossils. Some scientists theorize that in the deep subsurface, where pressure and geothermal heat create pockets of liquid water, microbial life might persist even today, descendants of those ancient coastal organisms, adapted to survive in a dying world. The race to find living Martian life has begun. And it all started with a small Chinese rover, detecting the ghost of an ancient shoreline, preserved in time. Thanks for watching, and thanks to our crew of astronauts over at Patreon who help us make scientific knowledge freely accessible to everyone. Chasing social media algorithms can be unpredictable. Your contributions help us continue creating the content we're passionate about. If you'd like to join our Patreon community, there's never been a better time to become part of the mission. Just follow the link in the description. When you join, you'll gain access to the entire video ad-free. See your name in the credits and submit questions directly to our team. The discoveries we discussed today represent some of the most exciting developments in planetary science. While the climactic ice drilling mission and fossilized life discovery are projections of where this research might lead us, the foundation, Zhurong's detection of ancient shorelines and the debate over Martian oceans, is very real and ongoing. Science is a story still being written, and we're all privileged to witness it unfolding. 6 months after the initial fossil discovery, the research teams made an observation that nobody anticipated. Dr. Yuki Tanaka, a molecular biologist analyzing the chemical signatures from the Martian samples, noticed something extraordinary in the genetic material fragments they'd extracted from the fossilized cells. The DNA-like molecules from Mars didn't use the same base pairs as Earth life. While Earth's DNA uses adenine, thymine, guanine, and cytosine, the Martian biomolecules incorporated additional base pairs, 6 in total instead of 4. This meant Martian life had independently evolved a more complex genetic code. It's like discovering that an alien civilization doesn't just speak a different language. Dr. Tanaka explained during a hastily arranged press conference. They use an entirely different alphabet with more letters than ours. The implications are staggering. This discovery obliterated the panspermia hypothesis, the idea that life on Mars and Earth shared a common origin through meteorite exchanges between the two planets. Martian life wasn't related to Earth life at all. It had originated independently, evolved along its own unique pathway, and developed its own sophisticated biochemistry. Life, it seemed, was not a cosmic accident. It was an inevitability. Give a planet liquid water, the right chemistry, and enough time, and life will find a way. But the revelations didn't stop there. In October 2027, the MLI rover's seismic sensors detected something unexpected: rhythmic vibrations deep beneath the Martian surface. At first, scientists dismissed them as geological activity, minor Mars quakes or thermal contraction. But the patterns were too regular, too organized. Dr. Marcus Webb, a geophysicist specializing in subsurface detection, spent 3 weeks analyzing the data. The vibrations occurred in clusters, separated by periods of silence, and always originated from the same depth, approximately 3 kilometers below the surface, right at the boundary where theoretical models predicted liquid water might exist due to geothermal heating and pressure. I've studied seismic data from volcanic regions, tectonic zones, and glacial systems on Earth, Webb said, his voice barely steady. These signatures don't match any geological process I know, but they do match something else: biological activity. Specifically, they match the vibrations created by microbial colonies metabolizing, growing, and producing gas as a byproduct. The scientific community reacted with extreme caution. The claim was extraordinary. Not just that Mars once had life, but that life might still exist there, hidden in subsurface aquifers, surviving the dark for billions of years after the surface oceans disappeared. NASA's chief scientist, Dr. Patricia Rodriguez, assembled an emergency review panel to assess the findings. After 6 weeks of intense scrutiny, examining every possible alternative explanation, the panel reached a careful conclusion. While we cannot definitively confirm living organisms without direct sampling, the data is consistent with active biological processes. Further investigation is warranted as a matter of highest scientific priority. The announcement triggered what journalists called the second space race. But unlike the Cold War competition between superpowers, this was a collaborative sprint involving nations and organizations worldwide, all united by a singular goal: reach the Martian subsurface aquifers and determine if life still thrives there. The challenge was immense. Drilling 3 kilometers into Martian bedrock would require technology that didn't yet exist. The drill would need to be autonomous, powerful enough to penetrate solid rock, yet precise enough to avoid contaminating any potential biosphere. It would need to operate in extreme cold, maintain sterile conditions, and carry sensors capable of detecting life in real time. Engineers from 12 nations collaborated on what became known as the Deep Reach Initiative. They developed a revolutionary drilling system using laser-assisted excavation combined with traditional mechanical drilling. The system could sterilize each new section of borehole with ultraviolet radiation before proceeding, ensuring that any life detected would genuinely be Martian, not Earth contamination hitching a ride on a spacecraft. The drill rover, aptly named Orpheus, launched in March 2029 with a price tag of $8.7 billion, the most expensive robotic mission ever attempted. But public support was overwhelming. People worldwide donated to the mission through crowdfunding campaigns. Children wrote letters to mission control. The world watched and waited. Orpheus landed in Utopia Planitia in October 2029, positioning itself directly above the strongest seismic signals. The drilling began on November 15th, broadcast live to millions of viewers across Earth. Progress was agonizingly slow, just 2 to 3 meters per day. The drill had to stop frequently to analyze core samples, conduct seismic surveys, and allow its systems to cool. Each evening, mission controllers reviewed the day's data, looking for any signs they were getting close. At 1.2 kilometers depth, the drill encountered a layer of clay minerals, the type that forms in the presence of water. At 1.8 kilometers, temperature sensors detected a significant thermal anomaly, suggesting underground heat flow. At 2.4 kilometers, moisture detectors registered increasing humidity in the borehole. They were getting close. On January 9th, 2030, 56 days after drilling began, Orpheus reached a depth of 2,847 meters. Suddenly, drill resistance dropped dramatically. The bore had broken through into a cavity. Mission controllers initiated immediate protocols. Cameras lowered into the cavity revealed a sight that took everyone's breath away. A vast underground chamber, its walls glistening with moisture. And there, pooled at the bottom of the cavity, reflecting back the lights of the probe, was liquid water. Liquid water. On Mars. Today. Not billions of years ago. But right now. The probe carefully extracted a water sample using sterile collection tubes. The liquid was brought into the onboard analysis chamber, sealed from the Martian environment, and subjected to a battery of tests. Within minutes, the first results arrived. The water contained dissolved salts, organic compounds, and most remarkably, free-floating particles that moved in patterns inconsistent with simple Brownian motion. Dr. Rodriguez, now serving as mission director, authorized the use of probe's most sophisticated instrument, a holographic microscope light detector, capable of imaging objects as small as 50 nanometers and determining whether they exhibited characteristics of living cells. The microscope activated. Images began streaming back to Earth, and there, swimming in the Martian water sample, were organisms. They weren't fossilized. They weren't ancient. They were alive. The cells were unlike anything on Earth, elongated, with multiple undulating membrane structures that propelled them through the water. They clustered in small groups, seeming to communicate through chemical signals. Some appeared to be absorbing minerals from the water. Others were dividing, reproducing before the camera's lens. "They're extremophiles," Dr. Chen whispered, tears streaming down her face as she watched the live feed. "They've adapted to survive in complete darkness, living on chemical energy from the rocks, thriving in conditions we thought were impossible." Mars didn't just have life. Mars still has life. Over the following weeks, Orpheus collected hundreds of samples from different depths within the aquifer system. Each sample revealed new species, or what appeared to be species, though the concept might not apply the same way to Martian life as it does to Earth life. Geneticists working with the biochemical data identified at least 17 distinct lineages of organisms, each with variations in their 6-base genetic code. Some were simple, barely more complex than Earth's most primitive bacteria. Others showed surprising complexity, cellular structures that suggested specialization, potential multicellularity, even primitive colony behavior. Dr. Tanaka's team made an astonishing discovery. One lineage of Martian microorganisms appeared to use a form of photosynthesis, even though they lived in total darkness. But instead of capturing energy from sunlight like Earth plants, they captured energy from a faint infrared radiation emitted by warm rocks in the aquifer. It was photosynthesis reimagined for a lightless world. Life doesn't just find a way, Dr. Tanaka reflected during a documentary interview. Life finds every way, every possible pathway, every energy source, every environmental niche. If life can exploit it, life will exploit it. The discovery raised profound questions about the diversity of life possible in the universe. If Mars alone harbored life with fundamentally different biochemistry, living in environments we thought were barren, how many forms of life might exist on the billions of potentially habitable worlds throughout the galaxy? The discovery of living Martian organisms triggered intense ethical debates. Some argued that humans had a responsibility to protect this alien biosphere at all costs, declaring Mars off-limits to colonization. Others countered that humanity's expansion into space was inevitable and necessary for our species' survival, and that we could coexist with Martian life through careful management. The United Nations convened an emergency session to establish the Mars Life Protection Treaty in July 2030. The treaty designated Utopia Planitia and surrounding regions as a protected biosphere, the first extraterrestrial nature preserve. Strict protocols were established for any future missions. No human presence within 500 kilometers of known aquifer systems, mandatory sterilization procedures for all equipment, and continuous monitoring for any signs of contamination. But the treaty also authorized continued robotic exploration and research. Scientists were determined to understand everything they could about this alien biosphere. How long had it survived underground? Had it descended from the ancient coastal organisms, or evolved separately after the oceans vanished? Could it teach us how life might persist on other worlds, even after surface conditions became hostile? Perhaps most profound was what the discovery meant for humanity's understanding of itself. For all of recorded history, humans had wondered if we were alone. Now we knew. We shared our solar system with another form of life, one that had existed alongside us for billions of years, separated by the cold vacuum of space, yet connected through the universal laws of chemistry and evolution. In September 2030, the International Academy of Sciences organized a global broadcast, the largest coordinated viewing event in human history. Over 6 billion people tuned in as the world's leading scientists, philosophers, and leaders reflected on the discovery. Today, we take our place in a larger community, said Dr. Rodriguez, her words transmitted across Earth and beamed toward the stars. We are not alone. We were never alone. Life is woven into the fabric of the cosmos, as fundamental as gravity or light. And now, as we look outward to the hundreds of billions of planets in our galaxy, we do so with new certainty. We are searching for family. The camera feed switched to a live image from Orpheus, deep beneath the Martian surface. The microscope showed a cluster of Martian cells, pulsing with life in their eternal darkness. Simple organisms, yet representing something infinite. The proof that life's spark can ignite anywhere, persist through anything, and endure against all odds. On Mars, beneath ancient shorelines where waves once crashed and life first bloomed, that spark still burned. And in discovering it, humanity had glimpsed not just our past, but our future among the stars. As we close this chapter of the Mars story, new questions emerge faster than we can answer the old ones. Teams are already designing missions to other promising locations on Mars, the polar ice caps, ancient river deltas, and other suspected aquifer systems. Each might harbor its own unique ecosystem, its own evolutionary experiments running in isolation for billions of years. And beyond Mars, scientists are looking with renewed urgency at Europa, Enceladus, and Titan, worlds with subsurface oceans that might hide biospheres dwarfing anything we found on Mars. If life could survive in the harsh underground waters of Mars, what might thrive in the vast dark oceans beneath the ice shells of Jupiter's and Saturn's moons? The story that began with Zhurong detecting ancient shorelines has evolved into something far grander than anyone imagined. It's no longer just about understanding Mars's past. It's about recognizing life's resilience, its creativity, and its apparently universal nature. The shores of Mars, once teeming with microbial life, may be dry now, but the life that flourished there never truly disappeared. It adapted, retreated, and endured, waiting billions of years in the darkness until curious visitors from Earth finally came looking. And in finding them, we found ourselves, not as lonely wanderers in an empty universe, but as one branch on a tree of life that grows throughout the cosmos, reaching toward the light of distant stars. The search continues, the discoveries await, and humanity's greatest adventure has only just begun. Thanks for watching, and special thanks to our crew of astronauts over at Patreon who make this content possible. Your support allows us to explore these incredible stories and share them with millions around the world. If you'd like to join our community and get exclusive behind-the-scenes content, early access to videos, and the chance to suggest topics for future episodes, check out the link in the description. Remember, we live in an age of discovery. Every day, scientists are making breakthroughs that reshape our understanding of the universe. The future we've imagined today, missions drilling deep into Mars, discovering living organisms in subsurface aquifers, is closer than you might think. The technology exists. The will exists. All that remains is time. Stay curious, keep looking up, and never stop asking questions. That's what makes us explorers. That's what makes us human. I'm Alex McColgan, and this has been Astrum. I'll see you next time as we continue our journey through the wonders of our cosmos.